Okay, so in this short video, I will like to explain to you guys how can we model uh, pre-stressing tendons in CSiBridge. So the first thing in modeling tendon in CSI is that you should have the tendon profile. This is a bridge, balance cantilever bridge, and I am going to show you how can we model tendon profile for uh, one of the span. So I will model tendon profile for this span. So let me rotate this. Okay, so I will model these tendons. One of these tendons, the rest you can process is same. So the first thing in defining tendon is that you should have the drawings of the bridge. So these are the drawing of the particular span which I am going to model. These are the five tendons in the span, and these are the profile data. So here in the drawing you can see that we have Y and Z. So Y stands for the vertical profile, vertical location of tendon along the span, and Z stands for the horizontal profile. So these are the location of tendon along the girder, and these are the coordinates or coordinates of the tendon. So at the start, as you can see, so uh, here in this drawing, the 0 0 start from the uh, center of the girder. So as you can see that the 0 0, it has a eccentricity of 150, or the location of 150 from the bottom. So 150 from the bottom comes out here. So it at the midpoint, it is at lowest position to produce maximum effect. So the tendons in this girder are 12 number 5. So 12 number 6, sorry, 12 number 6 mean that they are number 6 dia tendons of 12 numbers in each strand. So each of these strand contains 6 12 number 6. Number 6 is basically a type of tendon which has a diameter of number 6. It is not like rebar. There are two types of tendons, number 6 and number 5. So each of the tendons have 12 number 6 strands. Okay. So first of all, to define tendons, you have to define material properties. So uh, we will come to the tendons, and ASTM 416 is the most used, and grade 270. So we are using high grade. So these we have two grades, grade 250 and grade 270. But in this bridge, we are using grade 270. Okay. So after defining the material properties, what we have to do, we have to come to the bridge tab. In the bridge tab, in the pre-stress tendons, you will define a new tendon. These are all the tendons which I had previously defined for this bridge. So let's suppose I want to define a new tendon. So I will uh, 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 click on the add new tendon. So this window will open. First of all, I have to specify to the software for which span I am going to define the tendon. I am defining it for the start span, so it will start from the start abutment, and P1, this is P1, this is start abutment, and it will end at this span. So I will select this, so this span will come pop up in this small window. The second thing is you have to specify what type of stressing is going to be done. So either we are stressing it from the start or from the both sides. So in pre-stressing, or basically this is a post-tension bridge. So in post-tensioning, what we do, we can stress from both sides. Also we can stress from single side, either from the start and from the end, depending upon the design. In this span, we are doing it from the start because it is going to be stressed at the top, and we cannot accommodate equipment here, so we will have to stress it from this location. Okay, so after specifying the checking, we have to define the number of strand tendon area. So a tendon area is that how number of tendon area is depend upon the number of strand. So as you can see in the drawing, there are 12 number 6 strands, so you can add it from here. So this is there are strand types. So first of all we are using number 6. So this comes out to be 15 mm dia and 0.6 ASTM. This is the nominal diameter. Strand per tendon. So as I showed in the drawing, there are 12 strand per tendon. Okay, number of tendon is 1. So use area. So this area is automatically calculated by the CSiBridge. This use leave it as default. Okay. So after this, you have to define the force, the stressing or the jerking force. To define jerking force, we have two options. Either we can define the force or we can define the stress. So I will recommend that you should define the stress because it will automatically calculate the force for you, CSiBridge, by multiplying the stress with the area. So it is recommended that you guys should select the stress option. So the stress option is that, as you know that the ultimate stress of this tendon is 270 psi. So we usually stress the tendons up to 75% of its ultimate strength, which is also recommended by ASTRO. So what we going to do that, I will change the unit to kip per inch. Okay. So stress is 0.75 multiplied by 270. Okay. Modify. I pressed enter, so it okay. 0.75 into 275. So this is the stress. So you just give this it the stress value and it will automatically calculate force from the stress in this area. So after defining the stress, uh, you have other options. You also have to deal with other options. One is either you want to model this tendon as a load or as an element. So if you are going to perform proper pre-stress analysis, then you have to select this as an element. But if just you want to see the effect of forces due to pre-stressing on the span or on the girder, you can select it as a load. So it is recommended that you guys should select model as an element because later on you are going to check the stresses in this section. So for that, if you define it as a load, the stresses will not be calculated. Um, okay. After defining this, you have to define the tendon profile. So as I showed you in the drawing, there are two profiles. One is horizontal profile along the z direction, and one is the vertical profile. So to define the vertical profile, you have to come here, vertical layout, edit vertical layout. Okay. So here you have different option. You can use these tabs to define your own tendon profile, or you can come to this quick start option and define a parabolic profile. So for example, I select this parabolic tendon profile. So it has automatically calculated tendon profile for me. But in this case, I am not going to use the automatic profile because in the drawing we are given the profile which we are going to use. So I will use the drawing for the calculation of tendon profile. I had already defined the profile for this type, for this span, so I will show you that how I have defined that. So this is the tendon number 7, for which this is modified show tendon. So this is the last tendon, or you can say the first tendon from the bottom. This is this tendon which I had defined. Sorry, this is the second number tendon. The last one is tendon number 6. This is the bottom tendon. So how are I'm going to define the tendon profile. So first of all, you should come to the vertical layout. So you let me change the unit to Okay, so I will define tendon profile for this tendon number 5. So this is the tendon profile uh, for all of the tendons, and tendon number 5 is this. So you can see that the horizontal profile same remains constant, so the horizontally the tendon does not change position, but vertically it changes. It goes from 2903 to 750 at the center. Furthermore, in the next trend you see it starts from 3400. Start location is this is tendon number 5, so it starts from 3400 at a height of 3400 from the bottom, and uh, then it goes to according to this profile, starts from 3400 and then goes according to this profile. So the first thing in defining the profile is I will go to a tendon that I defined previously. Okay, vertical layout. Okay, so in the drawings, the profile is given from the bottom. So the profile starts from the vertical location. The origin is at the bottom of the girder, but in CSiBridge, the origin is at the top of the section. So when you define profile, you have to put a minus sign here and minus this vertical profile from 4000, which is the depth of the girder, uh, to get to get the location here. So initially, as you see in the drawing, the initial location is at a height of 3400 from the bottom. So from top it will come out to be 3400 minus 4000, 3400 minus 4000, which comes out to be 600. So the first point is at minus 600. Modify. Similarly this one minus 600. Modify. Then we will come to this drawing. The second point it is 200, 13,000. So 13,000 means from this center 13,000 is at somewhere around here, which is 2,000 from this side. So as we are starting from here from the left side, so the next point will be 2,000. The vertical location is 2903 from the bottom. So the from top it will comes out to be 4,000 minus 2903 equal to 1097. So 2000 minus 1097, it will be linear change insert below. So this is the second point. Third point will be this one at 12,000 from the center. So from the left it will be at 3,000, and the vertical location is 2649. So 4,000 minus 2649 comes out to be 1351. So select this one, parabola intermediate point 3000 135. So this is the second point. Similarly, the third point will be 11,000 from the center, so from the right it comes out to be 4,000, and the vertical location is 2406. So 11,000 is 4,000 minus 1549. So 49 insert. This is the second. Third point will be at 10,000 from the center, so 5,000 from the left. The vertical location is 2176. 4000 minus 2176 equals 1824. So that's 5000 Okay, sorry, this should be parabola intermediate point. The circle is also fine, but parabola intermediate point is the best option. So modify. This is also parabola intermediate point. Modify. So in the same manner, you will define the profile for the whole tendon. So I will just leave it here. And you can see this comes out to be the profile after putting all this data in the vertical layout. So when you put all this data, this will be the vertical profile of the tendon. Okay. So the next step is horizontal profile. So when you first define the horizontal tendon profile, it will be somewhere around here. It will be at this location, at the center line of the section. But in the drawing, as you can see that the tendon is at a location of 2.75 from the center. So when you define a tendon, you will just define a linear profile because it does not change along the section. It remains on at the same location along the section, and offset it from the center by 275. If it is to the left, minus, and if it is at the right, so plus. So there are two set of tendons, one at the left and one at the right. I have named them tendon 10 and tendon 10-1. So you see the tendon 10-1 lies to the right, which is which just we have to shift the start and the end at an offset of 2725. So this is all about how we can define tendon profile. The next thing in tendons definition is the to define the loss parameter, design parameters and loss parameters. So design parameter is only it requires you the duct diameter, which is typically given in the drawings. If not given, so the okay, if not given in the drawing, so what you can do that it is recommended by the code of practice that you should two times the area of the tendons can be used for the diameter of the duct, or two times the diameter of the uh, two times the area of the duct tendons can be used to find the diameter of the duct. The next important point is the loss parameters. So when you define tendons, you also have to define losses because some losses occurs during stressing. So there are different ways to define tendons pre-stress losses. One is that you just give these three coefficients, which are based on design, and and also you calculate these losses: elastic shortening loss, creep loss, shrinkage loss, and speed relaxation loss, and provide the value here. So after doing this, the program will not calculate the losses for you. But if you want to calculate the losses by using CSiBridge, then we have to define time dependent properties for the material. So for that you have to define time dependent properties first. So for example, if I want to define the pre-stressing relaxation loss, so I will attendance, switch to advanced property display, modify show material properties, and here I will use the time dependent properties. So when I use the time dependent properties, this, and select OK, this will the software will calculate the losses for me automatically by, but for this you have to define construction stage analysis as well. So I will recommend that you guys calculate the losses manually and just put the losses here, put the losses values here. Here is a very there are different way for calculating losses, but one of the easiest and common way is this paper written by these two authors. You can download it. It is available online. So in this paper, there are some short equation for calculation of these four losses. So you calculate losses from this paper. Put the value here. The curvature coefficient is typically taken for 2, 5, but code has given values. You can choose any one of them. Wobble coefficient and anchor slip, these are also given in the code. So this thing is also requires a detailed study, but in this video I will just give you an overview how can you put the loss parameter. So for loss parameter, you put these three values and calculate the losses and put them here, enter the value here, and then the software will design the tendon based on these losses. And one thing more, if you use the force type option, so then also you will have to put the values yourself. Then the CSI will not calculate them from the time dependent properties. If you have defined them, it will not calculate. But for the stress type, for the load type of when you define it as, so when you define the tendon as element, so you can define the losses either from here or from the time dependent material properties. But when you model as load, then you have to define loss parameter here, define loss parameters here. Furthermore, when you define them, model these tendon as a load. So this tendon will physically not be modeled just like this. Will not be modeled by the CSiBridge. Only the forces will be applied to the section to see the effect of forces, and this tendon profile will not be modeled explicitly by the CSI software. So this is a very brief video about how we can model tendons in CSI. Thanks for watching.